Imagine trying to rewind everything, not just human history, not just the Earth, not just the Sun or the Milky Way or the first stars. Imagine rewinding the universe itself until galaxies unbuild themselves, stars dissolve back into gas, atoms break apart, light becomes trapped, and space becomes so hot and dense that the ordinary meanings of distance, direction, and time begin to fail. Then, imagine asking the most dangerous question in cosmology. What was here before all of that? Before the first atom? Before the first light? Before space had stretched into the enormous darkness we see today? Before clocks could tick in any way we understand? This question sounds simple, almost like something a child might ask while looking up at the night sky. But the deeper you follow it, the stranger it becomes. Because the Big Bang was not an explosion inside empty space. It was not a fireball thrown into a black room. It was not matter flying outward from one central point, leaving behind a crater where everything began. The Big Bang was the early expansion of space itself. And if space itself was changing, then asking what came before it may not be like asking what happened before a firework exploded. It may be more like asking what is north of the North Pole. The words sound understandable, but the map underneath them may have stopped working. Before we begin, if you enjoy calm journeys through the deepest questions in space, take a moment to subscribe to the channel, leave a like, and write in the comments where you are watching from, and what time it is for you right now. It is strange to think that people in different places, under different skies, at different hours of the night, can all look into the same universe and ask the same question. Tonight, you are watching the Just About Space channel, talking about what existed before the Big Bang and why it's terrifying. And to understand why this question is so difficult, we have to start with what the Big Bang actually means. When people hear the phrase Big Bang, it is easy to picture a single point in darkness suddenly exploding into space. That image is powerful. It feels cinematic. It gives the mind something simple to hold: a spark, a detonation, a beginning surrounded by emptiness. But that image is also misleading. The Big Bang was not matter exploding into a pre-existing void. It was the universe itself, in an extremely hot, dense state, expanding and cooling. Every region of space we can observe today was once compressed into a much hotter and denser condition. Distances between things were smaller. Radiation was more intense. Matter behaved differently. And as space expanded, the universe changed from something almost unimaginably energetic into the colder, darker cosmos we now live inside. The important part is this: the Big Bang does not tell us that everything came from one dot sitting somewhere in a larger room. It tells us that the observable universe was once in a hot, dense, rapidly expanding state. That sounds like a small distinction, but it changes the whole question. Because if there was no outside room, then the universe was not expanding into something the way smoke expands into air. Space itself was stretching. The ruler was changing. The distance between faraway regions was growing because the geometry of the universe was evolving. So when we ask what existed before the Big Bang, we are not asking what was on the other side of an explosion. We are asking whether time, space, energy, and physical law had some earlier form. And that is where the fear begins. Not a monster kind of fear. Not the fear of something attacking Earth. A quieter fear. The fear that the word before may not belong there at all. We live inside time so completely that it feels impossible to imagine existence without it. Every thought we have is arranged in order. First, then, later. Yesterday, now, tomorrow. Even when we imagine eternity, we usually picture an endless line of time extending forever in both directions. But modern cosmology forces us to consider a more difficult possibility. Time may not be an eternal background. Time may be part of the universe. If that is true, then the Big Bang was not simply an event that happened in time, it may have been the edge of time as we understand it. The beginning of the clock, not just the first tick after an earlier silence. This does not mean scientists know that time literally began at the Big Bang. The honest answer is that our best-tested theories become incomplete when we push them too far back. General relativity, which describes gravity and the large-scale structure of the universe, points toward a state of extreme density if we extrapolate backward. Quantum physics, which describes matter and energy at tiny scales, tells us that reality becomes uncertain and restless at microscopic levels. But we do not yet have a complete theory that joins them cleanly under the extreme conditions of the earliest universe. So the beginning is not a clear photograph. It is a border where our current maps start to tear. To see why, let us rewind the universe in the safest way we can, using evidence. When we look into deep space, we are also looking backward in time. Light takes time to travel. The moon is seen as it was a little more than 1 second ago. The sun is seen as it was about 8 minutes ago. The nearest stars are seen years in the past. Distant galaxies are seen millions or billions of years ago. Telescopes are not only machines for seeing far away, they are machines for seeing earlier. And when we look far enough, we see that galaxies in the distant universe are younger. They are smaller, more chaotic, and often rich in star formation. Farther back, the universe becomes filled with glowing gas and early structures still assembling. Even farther, there is a wall of ancient light called the cosmic microwave background. This light is not from a star. It is the cooled remnant of the time when the universe first became transparent. For hundreds of thousands of years after the Big Bang, the universe was filled with a hot plasma. Electrons and atomic nuclei were not yet calmly joined into neutral atoms. Light could not travel freely for long because it kept scattering off charged particles. The universe was not dark in the way deep space is dark today, but it was opaque. It was like being inside a glowing fog with no clear view through it. Then, as the universe expanded and cooled, electrons joined with nuclei to form atoms. Light was finally able to move freely across space. That ancient light has stretched with the expansion of the universe for billions of years, cooling from visible and infrared wavelengths into microwaves. Today, it arrives from every direction as the cosmic microwave background. It is one of the greatest pieces of evidence we have that the universe was once hot, dense, and very different from the universe we see now. But it is also a wall. We can see the afterglow of the early universe, but not with ordinary light beyond that fog. Before that moment, the universe was opaque. The CMB is like a baby picture of the cosmos, but not a picture of its birth. It shows the universe when it was already hundreds of thousands of years old. So if someone asks what happened before the Big Bang, we cannot simply point a better telescope and watch it happen. Light itself refuses to carry that image to us. This is one of the first terrifying truths. There may be parts of cosmic history that cannot be seen directly with light at all. We can infer, we can calculate, we can test predictions, we can search for traces in patterns left behind. But the earliest moments are hidden behind conditions that break the ordinary method of astronomy. It is like trying to understand a storm by studying ripples left in mud after the clouds have already disappeared. The evidence is real. The traces matter, but the thing itself is gone from direct view. Now, if we continue rewinding past the cosmic microwave background, we enter earlier and earlier stages. The atoms disappear. The universe becomes a plasma again. Then atomic nuclei are broken into protons and neutrons. Go earlier, and even protons and neutrons become a soup of quarks and gluons. Go earlier still, and the energies become so high that the forces of nature may have behaved differently from how they do now. The universe was not simply a smaller version of today. It was a different physical environment. Particles that are rare or impossible to create naturally today may have been common. Forces that now seem separate may have been connected. Tiny quantum fluctuations may have been stretched into the seeds of galaxies. The smoothness of the universe, the structure of galaxy clusters, and the slight temperature variations in the cosmic microwave background all point towards something extraordinary happening very early. One of the leading ideas is called cosmic inflation. Inflation says that, extremely early in cosmic history, space expanded at an astonishing rate for a tiny fraction of a second. Not faster motion through space in the ordinary sense, but faster expansion of space itself. A region much smaller than an atom could have been stretched to a vastly larger size almost instantly, smoothing the universe and spreading tiny quantum variations across cosmic distances. This idea helps explain several puzzles. Why does the universe look so smooth on large scales? Why do far-separated regions have nearly the same temperature, even though they should not have had enough time to communicate by light? Why does space appear so close to flat in its large-scale geometry? Why do the slight imperfections in the cosmic microwave background have the patterns we observe? Inflation gives answers that fit many observations. It is one of the most powerful ideas in modern cosmology, but even inflation does not necessarily tell us what existed before the Big Bang. In fact, it pushes the mystery into a deeper place. What started inflation? What field drove it? Was inflation the beginning, or was it only a phase inside something older? Did it happen once, or could inflation keep producing many regions like ours? If inflation ended here, could it still be continuing elsewhere beyond what we can observe? These are not casual questions. They are questions about whether our entire observable universe is only a local event. Imagine a vast ocean of inflating space, with bubble-like regions where inflation ends and ordinary Big Bang evolution begins. Each bubble could become a universe with its own expanding space, its own matter, its own galaxies, perhaps even its own physical conditions. In that picture, our Big Bang would not be the absolute beginning of all reality. It would be the beginning of our region. This is sometimes connected to ideas of eternal inflation and the multiverse. But here we must be careful. The word multiverse can sound like fantasy, and many versions of it are speculative. Scientists do not have direct observational evidence of other universes. The idea comes from trying to understand what certain inflationary models may imply. It is not the same as saying we have discovered neighboring universes. We have not. Still, the possibility is unsettling, because it means the thing we call the universe may be only the part of reality that our history can reach. And if that is true, then asking what existed before the Big Bang may be like asking what ocean existed before the formation of one wave. The wave has a beginning, the ocean may not. Another possibility is that the Big Bang was not a beginning at all, but a rebound. In some bouncing universe models, the cosmos existed before in a contracting phase. Instead of starting from nothing, the universe may have been shrinking, becoming hotter and denser, until some process prevented a true singularity and caused a bounce into expansion. Our Big Bang would then be the transition from contraction to expansion. This idea is attractive because it removes the need for an absolute beginning. It gives the phrase "before the Big Bang" a more ordinary meaning. There could have been an earlier universe, perhaps old, perhaps vast, perhaps completely different from ours, collapsing toward a dense state. But bouncing models face enormous challenges. How does a universe contract without destroying all usable structure? What physics stops the collapse? How does the bounce avoid becoming a singularity? What survives through the bounce? Could any information from the previous phase leave an imprint in our universe? No one has a confirmed answer. A bounce is possible in some mathematical frameworks, but possibility is not proof. It is one road through the darkness, not a discovered landscape. There are also cyclic models, where the universe passes through repeated phases of expansion and contraction, or where Big Bang-like events occur again and again across vast timescales. In some versions, universes are born from collisions between higher dimensional structures. In others, cosmic history is a sequence of aeons, where the remote future of one universe somehow becomes the beginning of the next. These ideas are fascinating because they challenge our instinct that beginnings must be simple. But they also show how little certainty we have when we reach the earliest edge of time. The Big Bang model is extremely strong when it describes the universe after its earliest moments. It explains the expansion of space, the abundance of light elements, the cosmic microwave background, and the large-scale development of structure. But when we ask for the absolute first cause, we leave the well-lit road and step into theoretical territory. That does not mean anything goes. Science is not guessing wildly. Good models must make predictions. They must connect with observations. They must avoid contradicting what we already know. They must someday be testable, at least indirectly. But for now, the phrase "before the Big Bang" sits at the boundary between physics and mystery. And that boundary is not comfortable, because human beings are used to causes. A tree falls because wind pushed it. A fire starts because fuel ignited. A wave rises because energy moved through water. A child exists because parents existed before. A city exists because someone built it. Our minds expect every event to have an earlier event behind it. Cause and effect are the bones of ordinary thinking. So when we imagine the universe, we naturally ask, what caused it? But causality itself may depend on time. A cause comes before an effect. If time begins with the universe, then asking what caused time using earlier time becomes deeply confusing. It may be like asking what song played before sound existed. The question feels clear because grammar allows it, but physics may not. This is why the Big Bang is so terrifying in a quiet way. It is not just big, it is not just old, it is not just hot, or dense, or distant. It threatens the structure of explanation itself. At the edge of the beginning, our most familiar question may lose its usual meaning. Still, scientists keep looking for ways to push deeper. One possible messenger is gravitational waves. Light cannot show us the universe before it became transparent, but gravitational waves may carry information from much earlier times. Gravitational waves are ripples in space-time itself. We have detected them from events like black hole mergers and neutron star collisions. But a background of primordial gravitational waves, if it exists and can be measured, could reveal conditions from extremely early cosmic history. Such waves might carry clues from inflation, or from phase transitions in the early universe, or from other violent processes that happened long before the first atoms formed. They would not give us a simple movie of the Big Bang, but they could add a new sense to cosmology, as if the universe had been silent to our eyes, but not entirely silent to gravity. Another path comes from precision maps of the cosmic microwave background. The CMB is not perfectly uniform. It has tiny variations in temperature, slight differences from one direction to another. Those variations are incredibly small, but they are enormously important. They are the seeds of structure. Over billions of years, gravity amplified those small differences into galaxies, clusters, filaments, and voids. By studying the pattern of these variations, scientists can test models of the early universe. Different inflationary theories predict different patterns. Some versions might leave specific signatures in polarization, a subtle orientation in the microwave background light. Future measurements may narrow the possibilities. The universe may not show us the first instant, but it may have left fingerprints on the oldest light we can see. There is something almost eerie about that. The largest structures in the cosmos may come from the smallest possible disturbances, The galaxies we see today may be grown from quantum uncertainty. The Milky Way, Earth, and every living thing may trace back to tiny fluctuations stretched across space during a phase we still do not fully understand. If that is true, then the beginning of the universe was not smooth perfection. It was almost smooth, but not quite. And that not quite became everything. Too much smoothness and no galaxies form. Too much clumping, and the universe might collapse into black holes or chaotic structures before stable worlds can appear. The universe seems to have had just enough irregularity to become interesting. But why those conditions? Why those laws? Why that balance? This leads to one of the deepest versions of the before question. Not simply what existed before the Big Bang, but why did the Big Bang have the properties it had? Why did the early universe expand at the rate it did? Why did it contain the kinds of particles it contained? Why were the forces of nature tuned in the way we observe? Why was gravity strong enough to build galaxies, but not so strong that everything collapsed immediately? Why was the expansion fast enough to continue, but not so violent that matter could never gather? Some scientists hope these questions will eventually be answered by deeper physical law. Perhaps the conditions of our universe were not arbitrary. Perhaps they follow from a more fundamental theory. Perhaps there is only one mathematically consistent way for a universe like ours to exist. Others consider anthropic reasoning. Maybe many different regions or universes exist with different properties. We observe this one because it is compatible with observers. If the laws were too different, no stars, no chemistry, and no minds would arise to ask questions. This idea is controversial because it can feel unsatisfying. It explains our universe partly by selection effect. We are here because we are in a region where here is possible. That may be true, but it may not feel like the kind of explanation the mind wants. The mind wants a reason. Cosmology may offer a mechanism instead. And mechanisms are not always comforting. Now let us slow down and consider the word nothing. Many people imagine that before the Big Bang there was nothing, and then suddenly something appeared. But nothing is one of the most dangerous words in science and philosophy, because it can mean many different things. In everyday life, nothing usually means an empty room. But an empty room is not nothing. It contains space. It contains time. It contains quantum fields. It has dimensions, geometry, physical laws, and perhaps vacuum energy. It is a stage with no actors, but it is still a stage. A true nothing would be stranger. No space, no time, no fields, no laws in the ordinary sense, no possibility of location, no before or after, no emptiness, because emptiness itself requires a framework. When physicists talk about quantum vacuum, they are not talking about absolute nothing. A quantum vacuum is the lowest energy state of fields, but it is not empty in the philosophical sense. It can have fluctuations. It can have structure. It can produce effects. So if someone says, the universe came from nothing, we must ask, what kind of nothing? A quantum vacuum? A prior physical state? A boundary condition? A mathematical possibility? A timeless law? An absence beyond language? The terrifying part is that our words were built for objects inside the universe. They were not built for the origin of the universe itself. We can say before, outside, nothing, beginning, cause, and existence. But each word carries assumptions from ordinary experience. At cosmic origins, those assumptions may fail. This is not because the universe is trying to be mysterious. It is because our language evolved for survival on a planet. It evolved for food, weather, danger, memory, social life, and motion through familiar space. It did not evolve to describe a state where space-time may be quantum, where the distinction between geometry and matter may blur, and where causality itself may be incomplete. So part of the terror comes from scale. Another part comes from age, but the deepest part comes from mismatch. The human brain is trying to understand the conditions that made human brains possible. That is a strange loop. A tiny system inside the universe is trying to describe the earliest state of the universe using symbols created billions of years later by life on a rocky planet orbiting an ordinary star. And yet, somehow, those symbols work astonishingly well. Mathematics can describe the expansion of space. Equations can predict the abundance of helium. Measurements of microwave light can reveal the age and composition of the cosmos. Tiny fluctuations in radiation can explain the future locations of galaxy clusters. This is one of the most beautiful parts of cosmology. But it is also unsettling. We can understand more than we should intuitively be able to understand. We are not outside the universe, but we can still build models of its earliest visible states. Still, the models do not reach all the way. If we rewind using general relativity alone, the universe approaches a singularity, a state where density and curvature become infinite. But physicists generally do not treat that infinity as a physical object we have discovered. They treat it as a sign that the theory has been pushed beyond its domain. In other words, the singularity may not be a real place or moment. It may be the point where our math says, I cannot go farther with these tools. General relativity is one of the most successful theories ever created. It predicts the bending of light by gravity, the existence of black holes, gravitational waves, and the expansion of the universe. But it does not include quantum mechanics in a complete way. When the universe becomes extremely small and dense, quantum effects should matter. We need quantum gravity. Quantum gravity is not yet complete. There are candidates like string theory, loop quantum gravity, causal set theory, and other approaches. Each tries in a different way to understand the deep structure of space-time. Some suggest that space-time is not continuous all the way down. Some suggest that geometry itself may be emergent. Some suggest extra dimensions. Some suggest that the Big Bang singularity is replaced by a bounce or a quantum transition. But none has yet become the confirmed final theory. That means the question of what existed before the Big Bang depends partly on physics we have not finished. This is an important point for the script we are following tonight. We are not going to pretend to know what nobody knows. Instead, we are going to walk through the strongest possibilities, the evidence that guides them, the limits that block them, and the reasons the answer may be more disturbing than any simple beginning. Because the most frightening answer may not be that nothing existed. It may be that something did exist, but it was not time, space, matter, or reality in any form our minds can picture. Let us begin with the possibility that there was no before. This is the cleanest answer and in some ways the most difficult. If time itself begins with the Big Bang, then asking what happened before the Big Bang is not physically meaningful. The universe does not emerge after a previous moment. The first moment is simply the boundary of the timeline. This does not mean there was a dark eternity waiting and then the universe appeared. An eternity before time is already a contradiction. It means the timeline may be finite in the past. If you move backward, you eventually reach a boundary beyond which the concept of earlier does not apply. A common analogy is the surface of Earth. If you walk north, you eventually reach the North Pole. From there, asking which direction is further north does not make sense. The question uses a familiar word, but the geometry has ended the direction. In the same way, time may have a boundary, where asking what came before is like asking what lies north of north. But analogies can be deceptive. The North Pole exists on a larger surface. You can view it from space. You can see the whole globe from outside. With the universe, we do not have an outside vantage point. We cannot step out of time and inspect its boundary. We can only describe it mathematically and compare the predictions with observations. So even the no before answer is not simple. It may be true. It may be incomplete. It may be a clue that time is emergent, not fundamental. Emergent time is one of the strangest ideas in modern thought. It suggests that time, as we experience it, may arise from deeper relationships, perhaps from quantum entanglement, thermodynamics, or the way information is organized. In that view, time is not the basic stage on which everything happens. It is more like temperature. Temperature feels real. You can feel heat and cold, but temperature is not a fundamental object by itself. It emerges from the motion and energy of many particles. A single isolated particle does not have temperature in the same ordinary way a cup of gas does. Could time be like that? Could the flow of time emerge from something deeper, something timeless? If so, then before the Big Bang might be the wrong question, because before belongs to the emergent description, not the deeper level. At the deepest level, reality might not happen moment by moment. It might simply be, with time appearing only inside certain conditions. This idea is difficult because experience is temporal. You cannot think a thought without it unfolding. Even reading this sentence takes time. So imagining a timeless foundation is almost impossible. Every attempt turns into a sequence, because the mind builds sequences automatically. But physics has already shown us that intuition is not a reliable guide at extremes. At high speeds, time slows relative to other observers. Near strong gravity, clocks tick differently. At quantum scales, particles do not behave like tiny solid balls. In black holes, the geometry of time and space becomes twisted beyond ordinary experience. So perhaps at the origin of the universe, time is not what it seems. The terror here is subtle. If time is not fundamental, then our deepest sense of reality may be local. The flow from past to future, the feeling of becoming, the idea that the present is moving, may be a feature of our universe after it formed, not the foundation of existence itself. Everything we know happens in time. But the reason time exists may not be temporal. Now let us consider the opposite possibility. There was a before. If there was a before, then the Big Bang becomes not the absolute beginning, but a transition. Something existed, changed state, and became the universe we know. This may feel easier because it preserves causality, but it also opens a much larger abyss. What kind of previous reality could give birth to ours? One possibility is a contracting universe. Imagine the cosmos before ours expanding for a long time, then slowing, reversing, and collapsing. Galaxies draw closer. Radiation heats up. Space shrinks. The universe becomes denser and denser. But instead of reaching an infinite singularity, some quantum gravitational effect creates a bounce. The collapse becomes expansion. A new universe begins. In that picture, the Big Bang is not creation from nothing. It is cosmic rebound. There is something elegant about this. We know that extreme gravity can change the shape of space-time. We know that quantum effects become important at tiny scales. So perhaps a collapsing universe does not end in an infinite point, but in a new, expanding phase. The difficulty is entropy. Entropy is often described as disorder, but more precisely, it is related to the number of possible microscopic arrangements consistent with a large-scale state. In ordinary physics, entropy tends to increase over time. Broken cups do not reassemble. Heat spreads out. Stars burn fuel. Black holes grow. The universe appears to have an arrow of time. If a previous universe collapsed into ours, what happened to its entropy? Why did our universe begin in such a low entropy state? How can a bounce produce the smooth early conditions we observe? Can information pass through the bounce, or is it erased? These are not small technical details. They are central to whether a bouncing universe can work. Some models try to solve them. Others remain speculative. But the question shows how deep the problem goes. It is not enough to say the universe bounced. The bounce must explain why our universe looks the way it does. There is another possibility related to black holes. Some ideas suggest that new universes could form inside black holes. When matter collapses beyond an event horizon, perhaps instead of ending in a singularity, it transitions into a new expanding region of space-time. From the outside, the black hole remains a black hole. From the inside, a new universe could be born. This idea is not confirmed, but it is fascinating. If true, our universe might be the interior of a black hole formed in another universe. The Big Bang would be the other side of gravitational collapse. Every black hole in our universe might potentially contain another region of space-time, another cosmic branch. Again, we must be careful. This is not established science in the way the expansion of the universe or the cosmic microwave background is established. It is an attempt to understand what happens where general relativity predicts singularities, and quantum gravity should matter. But the image is powerful. A universe inside a black hole, a beginning born from collapse, creation hidden behind an event horizon. It turns the question around. Instead of asking why there is something rather than nothing, it asks whether universes reproduce through the most extreme objects they contain. There is a haunting logic to it. Stars die and make black holes. Black holes may hide new beginnings. A universe capable of making black holes might give rise to further universes. Cosmic death and cosmic birth become connected. But we do not know, and that uncertainty is important. The next possibility is even stranger. The universe may be part of a larger structure where Big Bangs happen repeatedly, but not necessarily in time the way we experience it. Some theories involving higher dimensions suggest that our observable universe could be a three-dimensional space embedded in a larger dimensional reality. In certain models, what we call the Big Bang could be related to the interaction or collision of higher dimensional brains. A brain is a kind of extended object in theories that go beyond ordinary three-dimensional space. This can sound abstract, because it is. But the rough idea is that our universe might be like a surface inside a higher dimensional arena. A cosmic collision or interaction could produce the hot, dense conditions we call the Big Bang. If something like this were true, then before the Big Bang there may have been a larger reality, not made of space in the way we understand. Our universe would be a slice, a membrane, a local event inside a deeper geometry. The terrifying part is not simply that there could be extra dimensions. The terrifying part is that our entire universe could be a surface effect. Everything we call space might be only part of a larger mathematical structure. Every galaxy, every atom, every memory, every future civilization might exist on a kind of cosmic sheet, whose origin comes from motions we cannot directly see. Again, these ideas are speculative. They are not proven, but they show that the question before the Big Bang does not have to lead to empty nothingness. It can lead to possibilities so large that the universe becomes smaller in comparison. There is also the idea of a quantum origin. In quantum physics, systems can behave in ways that do not match everyday cause and effect. Particles can appear and disappear in interactions. Fields fluctuate. Probabilities replace certainties. Events are described by wave functions and amplitudes, rather than simple mechanical paths. Some cosmological models imagine the universe as a kind of quantum event, perhaps tunneling from a state with no classical spacetime into an expanding universe. In such pictures, the universe may not need a cause in the everyday sense, because everyday causality belongs to the universe after classical time emerges. This can be deeply unsettling. If the universe can arise quantum mechanically, then the origin may not be like building a house or lighting a match. it may be closer to a transition from possibility to geometry. But even saying that risks sounding clearer than it really is. What is the quantum state of the universe? What does probability mean if there is no external observer? What is the background in which the wave function is defined? Can there be laws without time? Can there be a transition without before and after? These questions are not just philosophical decorations. They are part of the difficulty of applying quantum mechanics to the whole cosmos. In a laboratory, quantum physics usually describes systems within a larger world. There is a measuring apparatus, an environment, a clock, and an external context. But the universe has no outside lab. It includes the apparatus, the environment, the observer, and the clock. A quantum cosmology must describe everything. That is why the origin problem is so difficult. The universe is not just another object. It is the container of objects, or perhaps the network of relations that makes objects possible. When we ask where it came from, we are asking the container to explain its own edges. Now let us return to something more grounded. What do we actually know? We know the universe is expanding. Distant galaxies are generally moving away from us. And the farther they are, the faster their recession appears because space itself is expanding. This expansion implies that the universe was hotter and denser in the past. We know the cosmic microwave background exists, arriving from all directions as ancient cooled radiation. Its spectrum and tiny variations match the picture of a hot early universe with remarkable precision. We know the early universe produced light elements like hydrogen, helium, and traces of lithium in proportions that fit Big Bang nucleosynthesis. We know large-scale structure grew from small early differences under gravity. We know the universe is about 13.8 billion years old in the standard cosmological model. These are not guesses. They are pillars, but pillars do not automatically reveal the ground beneath them. The evidence takes us back very far, but not to absolute certainty about the first instant. The earliest fraction of a second remains an active area of research. Inflation is strongly motivated and supported in broad ways, but the specific mechanism remains uncertain. Quantum gravity remains incomplete. The nature of dark matter and dark energy is still unknown. So the honest scientific answer to what existed before the Big Bang is not one sentence. It is a map of possibilities surrounded by borders labeled unknown. And that honesty makes the topic more powerful, not less. A fake answer would be easy. A real answer must admit the edge. In this first half of our journey, we have reached that edge from several directions. From observation, we reached the cosmic microwave background and the opaque early universe. From theory, we reached inflation and the questions it leaves behind. From relativity, we reached the possible boundary of time. From quantum physics, we reached the possibility that space-time itself emerged from something deeper. From speculative cosmology, we reached bounces, cycles, black hole births, higher dimensional collisions, and multiverse-like landscapes. Each path gives a different image, a beginning with no before, a rebound from an earlier cosmos, a quantum event, a bubble in an inflating sea, a universe born inside a black hole, a surface in a higher dimensional reality, a cycle with no final first moment. None of these is simple. None is fully confirmed. And none gives us the kind of comforting answer that everyday experience expects. Because the Big Bang is not only an event in the past, it is a limit to vision, a limit to language, a limit to the current physics, a limit to the instinct that every question must have an answer shaped like the world we already know. And perhaps the most terrifying possibility is not that there was nothing before the Big Bang. It is that there was something so unlike space, time, matter, and causality that calling it before may already be wrong. To go farther, we need to look at the possibilities one by one, not as fantasy, but as serious attempts to understand what the universe may have been hiding at its own beginning. And the first of those possibilities is the one that removes the beginning entirely. That possibility is sometimes harder than a multiverse, harder than a bounce, and harder than a cosmic ocean of universes, because it does not give the mind an earlier scene to imagine. It does not give us a dark room. It does not give us an older star. It does not give us ancient ruins from a previous cosmos. It gives us a boundary where the question changes shape. Think about the way a movie begins. Before the first scene, there may be actors, cameras, scripts, studios, lights, and a director. The movie begins, but the world that made the movie existed before it. Our experience trains us to expect beginnings to be like that. Every beginning in ordinary life belongs to a larger setting. A building begins, but the ground existed before it. A storm begins, but the atmosphere existed before it. A life begins, but biology and the planet existed before it. A star begins, but gas clouds existed before it. So when someone says the universe began, the mind automatically asks for the larger setting. Where was it? What held it? What started it? What came first? But the universe is not a building, a storm, a life, or a star. It may not have begun inside a larger space. The larger setting may not exist in the same category. This is why cosmology can feel more disturbing than ordinary astronomy. Astronomy can give you objects, planets, moons, stars, nebulas, galaxies, black holes. Even when those objects are strange, they are still things inside a cosmic arena. The origin of the universe asks about the arena itself. And when you ask about the arena, every normal habit of thought becomes suspect. If time began with the Big Bang, there is no earlier physical moment in our universe to point to. There is no empty waiting period. There is no cosmic silence before the first sound. The silence itself would require time. Waiting requires duration. Duration requires time. Without time, there is no waiting. This is why the phrase "before time" is so difficult. The words create an image, but the image smuggles in the thing it is trying to remove. To imagine before time, you usually imagine a long, empty stretch. But a long, empty stretch is time. To imagine nothing happening, you imagine a period during which nothing happens. But a period is time. To imagine the universe waiting to begin, you imagine a clock that has not yet started, but even that clock is an image inside time. The mind is trapped by its own tools. And yet, the know-before possibility may not be meaningless. It may be exactly what a deeper physics requires. Some cosmological models replace the singular beginning with a rounded boundary. In these ideas, the earliest universe may be finite, but without a sharp edge in the ordinary sense. The past does not extend forever. But it also may not begin with a singular point where laws completely fail. Instead, time may behave more like a dimension that changes character near the origin. This is difficult to visualize, but the goal is to remove the infinite singularity while still preserving a universe with no earlier classical time. If such a model were correct, then the universe would not need a cause before it in the ordinary sense, because ordinary before would not exist. It would be self-contained, not because it floats in nothing, but because the question of external time would not apply. This can sound almost peaceful until you think about it carefully. A self-contained universe gives no outside explanation, no previous scene, no older clock, no hidden place where the reason waits. It simply exists as a whole physical history. For many people, that is more frightening than a violent beginning. A violent beginning still gives the mind something dramatic to imagine. A timeless boundary gives it almost nothing. But perhaps the mind should not demand comfort from the early universe. The cosmos is not obligated to be understandable in the way a campfire is understandable. It is not built around human narrative. It does not have to begin with a familiar cause. unfold with familiar logic, and end with a familiar lesson. It can be stranger than story. Still, the fact that we can even approach the question is extraordinary. We are not completely helpless. We can measure the universe. We can test ideas. We can reject models that do not match observations. We can say some things with confidence. For example, we can say that the early universe was not chaotic in every possible way. If it had been wildly irregular on large scales, the cosmic microwave background would look very different. Instead, the early universe was remarkably smooth, with tiny variations. Those variations were enough to form structure, but not enough to destroy the overall order. This smoothness is one of the clues that inflation tries to explain. Without inflation, distant regions of the observable universe appear to have nearly the same temperature, even though, in a simple Big Bang picture, they should not have had enough time to exchange information. Inflation solves this by saying those regions were once extremely close together before space expanded dramatically. That means the universe we observe today may have been shaped by a process that happened before the hot Big Bang phase we can model more directly. This is where terminology becomes important. Sometimes people use Big Bang to mean the absolute beginning. Sometimes they use it to mean the hot, dense, expanding state after inflation. Sometimes they include inflation as part of the Big Bang story. In popular language, these differences blur. In cosmology, they matter. If inflation happened, then the hot Big Bang may not be the first thing. There may have been an inflationary phase before the universe became the hot plasma that later produced atoms and the cosmic microwave background. But if we ask what came before inflation, the mystery returns. Inflation may be an early chapter, not page 1. This is why the question keeps moving backward. What caused galaxies? Tiny density variations. What caused those variations? Quantum fluctuations stretched by inflation. What caused inflation? Unknown. What set the inflationary field? Unknown. What made the field exist? Unknown. What made law itself possible? Unknown. Each answer opens a deeper question. That is not failure. That is how science advances. But at the beginning of the universe, the chain becomes especially hard because we cannot build another universe in a laboratory and watch its conditions vary. We have one observable cosmos, one cosmic history, one sky, one ancient background of microwave light, one set of galaxies, one pattern of large-scale structure. From that one universe, we try to infer what may be universal. This is like finding one shell on a beach and trying to understand every ocean. The shell contains clues. Its shape, chemistry, and growth lines matter. But it is still one object from one environment. The universe gives us more data than one shell, but it is still one universe from our point of view. This is why cosmologists search for hidden patterns so carefully. A tiny deviation in the cosmic microwave background, a particular pattern of polarization, a background of primordial gravitational waves, a statistical feature in the distribution of galaxies, a clue in the value of curvature, a mismatch between observations that might point to new physics. Any one of these could narrow the possibilities. Anyone could tell us whether inflation occurred in a certain way, whether the universe is finite or infinite, whether its earliest conditions came from a deeper mechanism. But the answer may remain partly beyond reach, and that is another terrifying possibility. Not that the answer is dark, not that the answer is strange, but that the answer may be permanently inaccessible from inside our observable region. The observable universe has a horizon. We can only receive light from regions whose light has had time to reach us since the early universe. Beyond that horizon, there may be more universe, perhaps vastly more, but its light has not reached us and may never reach us depending on cosmic expansion. If the key to the Big Bang lies in features beyond our observable horizon, then we may never see them directly. Our universe could be like a single room in a mansion, and the architecture of the whole building may be needed to explain why the room has the shape it does. But the doors are sealed by light speed, expansion, and time. This does not make science useless. It means science must work with what the universe allows. It means the oldest light, the largest structures, and the most subtle signals become precious. Every photon of the cosmic microwave background is ancient evidence. Every galaxy survey is a fossil map. Every gravitational wave detector is an attempt to give the universe another way to speak. The beginning may not be visible, but it may still be constrained. Now, let us think about why this question feels terrifying rather than merely interesting. Part of it is the collapse of scale. The Big Bang is not just far away, it is everywhere in the past. Every direction leads back to it. The matter in your body, the carbon in your cells, the oxygen in your blood, the calcium in your bones, and the hydrogen in the water inside you, all belong to a history that traces back to the early universe. You are not looking at the Big Bang from outside. You are made of its aftermath. The question is not only where did the universe come from, it is where did we come from at the deepest possible level. If there was no before, then your existence begins in a universe whose timeline has a boundary. If there was a bounce, then you are the descendant of an older cosmic collapse. If there was eternal inflation, then you may live inside one bubble among an immeasurable number. If universes form from black holes, then your sky may be the interior legacy of a dead star in a parent reality. If time is emergent, then your sense of past and future may be a local feature of a deeper, timeless order. Every option is strange. There is no ordinary answer waiting here. The safest answer is uncertainty. The most honest answer is that we do not yet know. But uncertainty does not mean emptiness. It means several doors remain open, and each door changes the meaning of reality. This first half of the journey has brought us to the threshold. We have seen that the Big Bang was not an explosion into space, but the early expansion of space itself. We have seen that the cosmic microwave background gives us a powerful but limited window into the young universe. We have seen that inflation may explain the smoothness and structure of the cosmos, while also raising deeper questions about what preceded it. We have seen that time itself may have begun, or emerged, or changed character near the origin. And we have seen that the word nothing may hide more confusion than clarity. So before we can ask what existed before the Big Bang, we have to choose what kind of answer we are prepared to recognize. A place, a prior universe, a quantum state, a timeless law, a field, a bounce, a boundary, a multiverse, a mathematical structure, or something for which our language has no clean category. The second half of this journey will move through those doors more slowly. We will examine the idea that our universe was born from a previous collapse, the possibility that black holes may be connected to cosmic birth, the strange logic of eternal inflation, and the unsettling thought that our Big Bang may not have been unique. And by the end, the question will not simply be what existed before the Big Bang. It will be whether the universe has a beginning at all, or whether beginnings are only what reality looks like from the inside. To move through those doors, we have to begin with one of the oldest images in cosmology, a universe that breathes, not a living creature, not a mind, not a machine with lungs, but a cosmos that expands, slows, collapses, and begins again. This idea is called a cyclic universe, and at first, it sounds almost comforting. Instead of one lonely beginning, there is a rhythm. Instead of a single impossible moment where everything appears, there is a previous chapter. The universe before ours may have grown old, emptied out, pulled itself inward, and then pass through some kind of transformation. What we call the Big Bang may have been the rebound from an earlier collapse. A bounce, a turning point, the end of one cosmic age becoming the beginning of another. This is not the standard picture in the simplest form of modern cosmology, but it has a long history because it tries to answer a question that the ordinary Big Bang model does not fully settle. If the universe was once hot and dense, why was it hot and dense? If everything was compressed into an early state, what placed it there? If space began expanding, what condition did expansion replace? A cyclic model says that maybe expansion replaced contraction. Imagine a universe filled with galaxies, stars, black holes, gas, dust, radiation, and dark matter. Over immense stretches of time, gravity works against expansion. In the simplest old version of the idea, the expansion slows, stops, and reverses. Galaxies that once fled from one another begin to fall back. The sky grows brighter not because stars are being born, but because all distances are shrinking. Radiation becomes hotter. Background light blue shifts. The universe becomes denser. Everything that had drifted apart is forced toward the same future. Then, eventually, the collapse reaches a state so extreme that normal physics fails. Instead of ending in a final singularity, the universe rebounds. Space expands again. Matter is reheated. A new cosmic cycle begins. That version is simple to picture, but the real universe has made it difficult. Observations show that cosmic expansion is not slowing enough to reverse. It is accelerating. The distant galaxies are not merely moving away. The expansion of space is speeding up on the larger scales. Dark energy appears to dominate the future, pushing the cosmos toward greater separation rather than collapse. So the old, simple, breathing universe picture does not fit what we currently observe. But the idea did not disappear. It changed. Modern bounce models do not always require the entire universe to collapse under ordinary gravity. Some use quantum gravity, the still unfinished attempt to describe gravity at the smallest and most extreme scales. Others suggest that a previous universe could contract in a way that avoids a singularity, because quantum effects create pressure at the final moment. Instead of infinite density, there is a limit. Instead of a mathematical breakdown, there is a bridge. This is one reason the question before the Big Bang is so hard. At normal scales, gravity is described beautifully by general relativity. It tells us how planets orbit, how light bends near massive objects, how black holes form, and how the universe expands. At tiny scales, particles and fields are described by quantum theory. It tells us about uncertainty, wave functions, vacuum fluctuations, and the strange behavior of matter when reality is examined at its smallest levels. But the early universe was both. It was gravitationally extreme and quantum extreme at the same time. That is where our best theories stop fitting together cleanly. A bounce might be real only if the missing theory, quantum gravity, allows it. And because we do not yet have a confirmed complete theory of quantum gravity, we cannot point to the sky and say with certainty that a previous universe collapsed into this one. Still, the idea is powerful. If a bounce happened, then before the Big Bang was not empty. It was not nothing. It was a universe in reverse, a cosmos moving toward compression instead of expansion. But that answer is not automatically less frightening, because a bouncing universe raises a colder question. How many times has this happened? Was there one previous universe, or an endless sequence? Did each cycle erase the last completely, or did faint information survive? Could the laws of physics change from one cycle to the next? Could the constants that allow atoms and stars to exist be reset each time? Is our universe one lucky throw after countless failed cycles? Or is there some deeper rule that makes universes like ours inevitable? The comfort of a previous chapter quickly becomes the dread of an infinite book. If the universe has bounced forever, then there may be no first page, no original morning, no earliest event, only cycles behind cycles, each one hidden behind a wall of heat, expansion, and lost information. And if every cycle destroys the evidence of the cycle before it, then the past may be infinite while remaining permanently unknowable. That is one of the first terrifying possibilities. The Big Bang may not be the start of everything. It may only be the last door that closed behind us. Another door leads somewhere even stranger. Black holes. At first, black holes seem like endings, not beginnings. They are regions where matter collapses so tightly that escape becomes impossible. Cross the event horizon, and every path forward points inward. Light cannot return, signals cannot climb out. The outside universe sees only a dark boundary around a hidden interior. But the interior of a black hole is one of the places where our knowledge breaks. General relativity predicts that matter falling inside may continue toward a singularity, a place where density becomes infinite and space-time curvature becomes unbounded. But most physicists suspect that an actual infinity is a warning sign, not a real object. It tells us that our theory has been pushed beyond its domain. If quantum gravity changes what happens at the center of a black hole, then maybe collapse does not end in a true singularity. Maybe it transitions. Maybe it opens into a new expanding region of space-time. In some speculative ideas, a black hole in one universe could give birth to another universe on the other side. From the parent universe, the black hole looks like a dark gravitational trap. From inside the newborn region, the same event might look like a Big Bang. This is not proven. It is not something we can test directly with current technology. But it forces the mind into a strange position. What if every black hole is not only a grave, but also a seed? What if our own universe began inside something that, from the outside, looked like a collapsed star in another reality? Then, before the Big Bang, there may have been a parent universe. Not just a previous cycle, but a larger cosmic environment in which black holes form. Each one carrying the possibility of a new space-time. The universe we know could be one child among many. Its laws might be inherited imperfectly from the conditions of the black hole that produced it. Its constants might be slightly altered. Its dimensions, particles, and forces might be variations in a cosmic family tree. That idea has even led to a speculative concept sometimes called cosmological natural selection. In biology, organisms that reproduce more successfully become more common. In a cosmic version, universes that produce more black holes would produce more baby universes. Over many generations, the constants of physics might drift toward values that make black hole production efficient. The thought is wild. It suggests that our universe may be shaped not by a designer and not by pure chance alone, but by a strange reproductive process on scales almost impossible to imagine. A universe that makes stars, stars that make black holes that make universes. And inside one of those universes, small creatures eventually ask where all of it came from. But even this does not give us the final answer. Because if our universe came from a black hole, then we can ask where the parent universe came from. If that parent came from a black hole in an older universe, then we are back to the same abyss as before. The explanation moves the beginning backward, or outward, or upward into a larger structure. It does not necessarily remove the mystery. It multiplies it. And there is another problem. A black hole hides its interior from the outside, and a newborn universe, if it exists, may be disconnected from its parent. No telescope inside our universe could simply turn around and look into the parent reality. No spacecraft could climb through the Big Bang and emerge where the parent star once collapsed. The boundary may be absolute. So the idea gives us a possible answer, but almost no direct access to the place where the answer would live. That is why before the Big Bang cosmology often feels like standing at a sealed window. You can see fingerprints on the glass. You can infer that something may be outside, but you cannot open it. At least, not yet. The next door is wider, and in some ways more unsettling. Eternal inflation. In the first half of this journey, we talked about inflation as a brief explosive expansion very early in the universe. A tiny region of space may have expanded faster than ordinary intuition can follow, smoothing and stretching the cosmos until it became large, flat, and nearly uniform. Inflation can help explain why distant regions of the universe look so similar, even though they seem too far apart to have exchanged information in the usual way. But inflation has a strange habit. In many versions of the theory, once inflation begins, it does not stop everywhere at once. It stops locally. A region exits inflation, cools, forms particles, radiation atoms, stars, and galaxies. That region becomes a universe like ours, or at least a bubble with its own cosmic history. But beyond that region, inflation may continue. Space keeps expanding at a tremendous rate. Other patches stop later. Those patches become other bubble universes. More regions inflate, more bubbles form. The process can continue without a single global ending. This is eternal inflation, and if it is true, then our Big Bang may not have been the beginning of all reality. It may have been the moment our local bubble stopped inflating and became hot. Our universe would be one bubble in an inflating background, one cosmic pocket among perhaps endlessly many. This idea changes the meaning of the word universe. In ordinary speech, universe means everything. All space, all time, all matter, all energy, all laws. But in eternal inflation, what we call the universe may be only our observable region, or our bubble space-time, while a much larger multiverse continues beyond any possible horizon. There may be other bubbles with galaxies, other bubbles with different physics, other bubbles where matter cannot form, other bubbles where stars burn differently, where dimensions compactify in other ways, where forces have altered strengths, where the chemistry needed for life never appears, or appears in a form we would not recognize. The terrifying part is not only that there may be more, it is that there may be no outer wall, no final container, no map on which all bubbles can be placed and counted. If inflation is eternal, creation may not be a single event in the past. It may be an ongoing process outside our cosmic reach. New universes may be forming forever, in regions that will never exchange light with ours. Then, the Big Bang becomes local weather, not the birth of all that exists, but the beginning of our particular region. A storm cleared, a bubble cooled, a domain began to evolve. From inside that domain, the event looks absolute. All our clocks lead back to it. All our galaxies emerged from it. All our matter was once compressed into its early furnace. But from a larger view, if such a view could exist, it might be one event among uncountable others. This is why the multiverse is both fascinating and controversial. It can explain why our universe has properties that seem delicately balanced. If there are enormously many universes with different constants, then it is not shocking that we find ourselves in one compatible with observers. We could not be in a universe where atoms fall apart immediately, or where stars never form, or where chemistry cannot become complex. This is called anthropic reasoning. It is simple and dangerous at the same time. Simple because it says observers can only observe places where observers are possible. Dangerous because it can become too easy. If every strange feature of our universe is explained by saying there are countless universes and we happen to be in a rare one, then explanation becomes less predictive. Science works best when ideas risk being wrong. A theory that can accommodate almost anything may be hard to test. Still, the multiverse remains difficult to ignore. because it appears naturally in some serious inflationary models, and because our universe already contains regions beyond observation. We know our visible universe is not necessarily all of space. The cosmic horizon limits us. There may be galaxies far beyond what we can see, simply because their light has not reached us, or never will. The multiverse extends that humility further. Not only might there be more universe beyond our horizon, there might be other histories, other Big Bangs, other cosmic laws, and no way to stand outside them all. This is terrifying in a different way from a black hole universe or a cyclic universe. A cyclic universe terrifies because it may have no first cycle. A black hole universe terrifies because our cosmos may be born from a hidden interior. Eternal inflation terrifies because it makes our entire cosmic origin look provincial, local. One bubble among many, not the central event of reality, but one cooling patch in a process too large to enter our sky. And yet, if eternal inflation is true, it may leave subtle traces. Some scientists have wondered whether collisions between bubble universes could leave marks in the cosmic microwave background. If another bubble brushed against ours in the early stages, it might imprint a circular pattern or a temperature anomaly. Researchers have looked for such signals. So far, nothing has provided accepted proof. The sky does not hand us a clear photograph of another universe. It gives us statistics, patterns, faint temperature differences, and the need for caution. That caution matters. The question of what existed before the Big Bang is too easy to turn into fantasy if every possibility is treated as equally likely. Some ideas are mathematical, some are philosophical, some are motivated by existing physics, and some are barely more than images. A good journey through this question has to keep one hand on wonder and the other on honesty. We can explore the doors. We cannot pretend every door has opened. Another possibility removes the word before almost completely. Maybe time did not exist in the way we understand it until the universe reached a certain state. This is not merely a verbal trick. In general relativity, time is not a separate stage on which the universe performs. Time is part of space-time. It is woven with space. Gravity changes the rate at which time passes. Motion changes time. Near a black hole, clocks behave differently from clocks far away. In an expanding universe, time is tied to the cosmic geometry itself. So when we ask what happened before the Big Bang, we may be asking for a time outside time, a north of the North Pole, a moment earlier than the first moment. In one family of ideas, the universe does not begin from a previous event. It begins as a boundary condition. The Big Bang is not a point where something explosive happens inside pre-existing time. It is more like an edge of time itself. That sounds abstract, but the analogy is useful. Earth has a North Pole. If you travel north, eventually you reach it. But once you are there, asking what is north of the North Pole does not describe another location on Earth. The direction has ended. The question breaks because the coordinate no longer works. Maybe time is similar near the origin. If you travel backward through cosmic history, you pass galaxies forming, stars igniting, atoms assembling, plasma cooling, nuclei forming, and then you approach a state where our usual concept of earlier becomes unusable. There may not be a prior minute, because minutes belong to the universe after time has taken its familiar form. This does not mean the universe came from nothing in the everyday sense. It means the question may not fit the territory. The human mind likes causes arranged in a line. One thing happens, then another thing happens because of it. A match strikes. A flame appears. A window breaks because a stone hit it. We carry that logic backward. If the universe exists, something must have caused it. If the Big Bang happened, something must have happened before it. But causation may require time. And if time itself is part of what begins, then a cause before time is not straightforward. Some physicists and philosophers have tried to imagine causation without time, or a deeper, timeless structure from which time emerges. But once we enter that territory, ordinary language becomes fragile. We use words like before, cause, event, state, origin, and beginning, but each word brings assumptions from daily life. The universe may not care about those assumptions. There are also models in quantum cosmology where the wave function of the universe describes possible cosmic geometries without requiring a classical before. The universe might be understood as a quantum object, not as a little thing floating in a larger room, but as the total system whose classical history emerges under certain conditions. In that picture, what existed before the Big Bang may be the wrong question. A better question may be, what deeper rule gives rise to a universe with time? That answer, if it exists, may not be a place or a previous cosmos or a cause in the ordinary sense. It may be a law-like structure, a quantum state, a mathematical relationship, or a set of possibilities from which a classical universe emerges. This is where the terror becomes quiet, because the frightening thing is not fire, not collision, not collapse. It is the possibility that reality at its deepest level is not built in the categories our minds are designed to use. We may be asking for a scene when the answer is an equation. We may be asking for a place when the answer is a boundary. We may be asking for a previous moment when moments themselves are part of the thing being explained. The Big Bang then becomes less like an explosion and more like a shoreline. On one side, we have time, matter, radiation, distance, temperature, history, and eventually stars. On the other side, the word side may not even apply. Still, there is another door, and it may be the most radical of all. Maybe the universe did not need a previous universe, a parent black hole, a timeless boundary, or an eternal inflating background. Maybe the universe began as a quantum event. In quantum physics, empty space is not truly empty. Fields remain, fluctuations occur, particles can appear and vanish in ways governed by uncertainty. But this does not mean that universes simply pop out of ordinary nothingness. Quantum vacuum is not nothing. It is a physical state with rules, structure, and behavior. When people say the universe may have come from a quantum fluctuation, the phrase can be misleading if it is heard as magic. A fluctuation requires a framework, a field, a set of laws, a background, or a deeper formal structure in which probability has meaning. So the question immediately shifts. If the universe arose from a quantum process, what gave that process its laws? Why those rules instead of others? Why is there a quantum structure at all? This is where physics touches philosophy. Not because science has failed, but because the questions become foundational. Science can describe patterns with extraordinary success. It can test predictions, measure radiation, map galaxies, and reconstruct the first minutes of cosmic history. But when we ask why there are laws rather than no laws, or why mathematical order exists, the answer may require a kind of explanation we do not yet possess. Some thinkers respond by saying, laws do not need an external cause. They simply are. Others say the laws may emerge from something deeper. Others suspect that asking why anything exists may be a question without a final scientific form. But the question remains, if before the Big Bang there was a quantum state, then why was there that state? If there was a multiverse-generating field, why was there that field? If time began as a boundary, why did the boundary have the properties that allowed a universe like ours? Every answer seems to reveal a deeper flaw underneath it. You step down, and the stairs continue. This does not make the search pointless. It makes it honest. A small child can ask why the sky is blue. A scientist can explain scattering. The child can ask why molecules scatter light that way. The scientist can explain electromagnetism. The child can ask why electromagnetism has those laws. The scientist can go deeper into quantum fields, symmetries, and constants. At some point, the answer reaches the edge of current knowledge. The child has not asked a foolish question. The child has discovered the depth of the world. The Big Bang question is like that, but with everything. Not why one event happened, why there is a stage on which events can happen. Not why one star ignited, why stars are possible. Not why the universe expanded, why there is something capable of expansion. And the reason this is terrifying is that the answer may not be emotionally satisfying. It may not be simple. It may not place human beings near the center of meaning. It may not even sound like an answer when translated into ordinary speech. A good scientific answer to the deepest origin may be colder than mythology, stranger than fiction, and less comforting than silence. But it would be real, or at least closer to reality than anything we have now. One of the most important facts about the Big Bang is that we can see after it, but not through all of it. The cosmic microwave background is sometimes described as the oldest light we can observe. It was released when the universe cooled enough for electrons and nuclei to combine into atoms, allowing photons to travel freely. Before that, the universe was opaque. Light scattered constantly. The early plasma hid its own interior. This means the universe gives us a curtain, not a brick wall, but a glowing surface beyond which ordinary light cannot show us more. To study earlier times, scientists use other clues: the abundance of light elements such as hydrogen, helium, and lithium, the distribution of galaxies, the tiny fluctuations in the microwave background, the behavior of large-scale structure, particle physics, gravitational waves, if primordial ones can ever be detected, mathematical consistency between theories and observations. Each clue reaches backward in a different way, but none simply photographs before the Big Bang. That is why primordial gravitational waves are so exciting. Gravitational waves are ripples in space-time itself. If inflation happened, it may have produced a background of gravitational waves, faint patterns that could leave an imprint in the polarization of the cosmic microwave background. Detecting such a signal would not show us before inflation directly, but it could reveal energies and processes far earlier than ordinary light can reach. So far, the search continues. There have been claims, excitement, corrections, and caution. The early universe is not easy to interrogate. Dust in our own galaxy can mimic signals. Instruments must be astonishingly sensitive. Statistical confidence matters. A beautiful result is not enough if it cannot survive scrutiny. This is another quiet strength of science. It does not only ask grand questions, it also waits, it checks, it admits when a signal may not be what it first appeared to be. And with the Big Bang, patience may be the only honest path. The universe is not required to make its origin obvious. It may take generations of better telescopes, better detectors, better particle theories, better quantum gravity, and better mathematical tools before we know which doors are real. This is why the subject is perfect for a long night of thought. Every answer has a shadow. If there was a previous universe, what began that one? If there was a bounce, why did the bounce happen? If black holes create universes, what is the full tree of cosmic ancestry? If inflation is eternal, are we trapped inside one bubble forever? If time began, how can existence be explained without before and after? If the universe arose quantum mechanically, what grounds the quantum rules? If the answer is a multiverse, why that multiverse? If there is no final reason, why does reality still obey such deep order? These questions do not cancel each other. They form a map of ignorance. And a map of ignorance is not failure. It is the shape of what remains to be understood. There is also a more personal reason the question feels terrifying. The Big Bang is not merely an event far away in time. It is the origin of the conditions that made every later thing possible. Every atom in your body belongs to a chain that runs back through stars, through early galaxies, through primordial gas, through the first nuclei, through the hot plasma, and into the first seconds of cosmic history. Before the Big Bang, if that phrase means anything, is before the stage on which your atoms could ever exist, before carbon, before oxygen, before planets, before chemistry, before memory, before clocks, before the difference between here and there had the meaning it has now. That is why the question reaches into identity. We are not outside the universe asking about an object. We are the universe asking about itself from the inside. The eyes looking toward the cosmic background are made from matter the universe produced. The mathematics used to describe inflation is written by brains built from elements forged in stars. The fear we feel before the unknown is an arrangement of atoms that did not exist when the oldest light was released. There is something almost impossible about that. A reality with no obvious need to become aware has produced beings who wonder about its origin. And yet awareness does not grant access to every answer. We can trace the story backward with astonishing success, but not all the way. We can name the limits, sharpen them, and sometimes push them farther. We can distinguish evidence from speculation. We can reject false certainty. But we cannot demand that the deepest beginning appear in human terms. That may be the most humbling part. The universe is not hiding from us like a puzzle maker leaving clues for a game. It simply is. Some clues survive because physics preserves them. Others are erased because expansion, heat, and horizon limits erase them. The past is not a complete archive. It is a damaged record, and some of the damage may be permanent. If a previous universe existed, the Big Bang may have destroyed its fingerprints. If other bubble universes exist, their light may never reach us. If time began, then asking for earlier evidence may be meaningless. If quantum gravity governs the origin, then our current instruments may be blind to the relevant layer of reality. So the terror is not that we have no ideas. We have many. The terror is that several of them are plausible enough to take seriously, strange enough to unsettle us, and remote enough that proof may remain difficult for a very long time. Still, the known universe gives us a foundation. We know it has been expanding and cooling. We know it was once hotter, denser, and more uniform. We know light elements formed early. We know the cosmic microwave background fills space as a fossil glow. We know structure grew from tiny fluctuations into galaxies and clusters. We know gravity shaped matter into the cosmic web. We know dark matter appears to have guided structure formation. We know dark energy now affects the long-term expansion. These are not guesses floating in darkness. They are pillars. The unknown begins beyond them, not instead of them. That distinction matters, because mystery is often abused. Some people hear that scientists do not know what came before the Big Bang and imagine that anything is equally valid. But not knowing the final answer does not erase what has been learned. The path backward is lit for a long way. The early universe is not a blank page. It is one of the most studied subjects in modern science. Its mystery is not weakness. Its mystery is what remains after enormous success. The terrifying part is not ignorance alone. It is educated ignorance, the kind that knows exactly where the wall stands, the kind that can describe the wall, measure the light on this side, test the cracks, and still admit that the other side is hidden. So what could have existed before the Big Bang? A collapsing universe may have existed, carrying the ashes of an older cosmos toward a bounce. A parent universe may have existed, with our space-time born through a black hole interior. An inflating multiverse may have existed, generating bubble universes without a global beginning we can identify. A timeless quantum state may have existed, from which time emerged as a property of our universe. A boundary may have existed, not before time, but at the edge, where time begins. Or the word existed may fail, because existence itself may not have the same meaning outside the conditions that shaped our cosmos. This is the hardest part to accept. The answer might not fit into the form of the question. Human curiosity often expects the universe to be like a story. A story has a first sentence, a first scene, a reason the curtain rises. If the Big Bang is not the first sentence, we want the sentence before it. If there is a previous page, we want the page before that. If there is a book, we want the author, the shelf, the room, the building. But reality may not be a story in that way. It may be a structure where some regions have time and some descriptions do not. It may be a process without a first event. It may be a system where beginnings are local transitions. It may be a mathematical object whose entire history is not generated step by step, but described as a whole. Or it may be something we have not imagined, because our imagination grew inside a universe with clocks, matter, and cause. This does not mean the search is hopeless. It means the search will change us. Every time humanity has pushed beyond an old boundary, the world became less centered on us and more real. Earth was not the center of the cosmos. The sun was not unique. The Milky Way was not the entire universe. Matter we can see is not most of what exists. Space is expanding. Time is flexible. The atoms in our bodies were made in stars. The Big Bang question may be another step in that same pattern. Maybe the universe is not the whole of reality. Maybe time is not fundamental. Maybe beginnings are not absolute. Maybe our cosmic history is one page in a library without visible walls. Or maybe, against all intuition, the Big Bang really is the edge, and there is no earlier thing to find. Each possibility removes a different comfort. A prior universe removes uniqueness. A multiverse removes centrality. A timeless origin removes ordinary causation. A quantum origin removes common sense. A true beginning removes the safety of asking what came before. There is no version that leaves the human mind untouched. But there is beauty in the fact that the question can be asked at all. Not sentimental beauty, not a simple reassurance, a sharper kind, the kind that appears when a small civilization learns to measure the oldest light in the sky, the kind that appears when mathematics reaches into errors no eye could witness, the kind that appears when uncertainty is not used as an excuse to stop thinking, but as a reason to think more carefully. The universe may not give us a final answer soon, but it has already given us enough to know that the question is real. We are not imagining the mystery. We are standing at the edge of one, and perhaps that is why it feels terrifying. Not because the Big Bang was an explosion, not because there was darkness before it, not because some monster waits outside time, but because the origin of everything may be deeper than the structure of human thought. It may be older than time, if older can mean anything there. It may be wider than universe, if universe is only our local word. It may be stranger than nothing, because nothing may not be simple enough. There is one more way to understand why this question refuses to settle. Every possible answer changes the size of reality in a different direction. A bounce makes reality deeper in time. A multiverse makes it wider in space or possibility. A black hole origin makes it nested. A timeless beginning makes it stranger than sequence. A quantum origin makes it less solid than instinct. None of these directions is easy to visualize, because the human brain is built for rooms, roads, faces, hunger, danger, weather, and memory. It is not built to picture a pre-geometric quantum state, or a space-time foam, or an inflating background where bubbles of cosmic history form outside one another forever. This is not an insult to the human mind. It is a reminder of where the human mind evolved. For most of our existence, the deepest practical questions were close. Where is shelter? Where is water? Which plants are safe? What sound moved in the dark? Which path leads home? The brain learned to survive at human speeds, under one atmosphere, on one planet, beneath one star. Then, only recently, that same brain began asking about temperatures in the first second after the Big Bang. It began measuring redshift. It began detecting gravitational waves from colliding black holes. It began mapping microwave radiation older than the Earth by more than 9 billion years. The fact that we struggle to imagine the origin is not surprising. The surprising thing is that we have reached the edge of the problem at all. But reaching the edge creates a special kind of danger. It becomes tempting to fill the unknown too quickly. A beautiful idea can sound true because it feels complete. A strange theory can feel profound because it is difficult to picture. A confident voice can make speculation feel like discovery. And when the subject is the beginning of everything, the temptation becomes even stronger, because people do not like leaving the largest question open. Yet an open question is not an empty one. It has boundaries. It has evidence around it. It has wrong answers that can be rejected. It has ideas that can be improved. It has predictions that may someday be tested. This is why the best answer tonight is not a single claim, but a careful ranking of what we know, what we suspect, and what we can only imagine. We know the universe expanded from a hot, dense, early state. We know the cosmic microwave background is real. We know early nucleosynthesis produced light elements in proportions that match observation. We know galaxies grew from tiny density differences. We know general relativity describes the large-scale behavior of space-time extremely well. We know quantum physics describes matter and fields with extraordinary accuracy. We suspect something like inflation may have happened, because it solves several deep puzzles and fits many observations. We suspect the earliest era requires quantum gravity, because classical gravity and quantum effects both become unavoidable. We can imagine bounces, multiverses, black hole births, no-boundary proposals, and quantum creation models. But we cannot yet say which, if any, describes reality before our observable history began. That layered honesty matters. It protects wonder from becoming misinformation. It keeps mystery from turning into a cheap answer. And it makes the subject more powerful, not less. Because the real universe has never needed exaggeration to be astonishing. Consider what would happen if a future experiment did find evidence for a bounce. Maybe a pattern in primordial gravitational waves shows that the early universe carried a memory of contraction. Maybe a specific distribution of fluctuations matches a model where a previous cosmic phase squeezed and rebounded. Maybe quantum gravity matures into a theory that predicts a bounce so precisely that the sky can test it. If that happened, the story of existence would change overnight. The Big Bang would no longer be the earliest physical chapter. It would become a transition. The question of origin would move into a deeper past. Cosmology would have to ask what the previous universe was like, how much of it survived, whether its arrow of time pointed toward the bounce or away from it, and whether countless older cycles lie behind ours. History would become prehistory. Cosmic archaeology would gain a hidden layer. Now imagine a different discovery. Suppose future observations found a convincing signature of a collision between our bubble universe and another. A circular pattern in the microwave background, supported by independent evidence, too clean and specific to dismiss as statistical noise or foreground contamination. That would be one of the most disorienting discoveries in human history. It would mean the universe is not alone in the deepest sense. Not merely that other galaxies exist or other planets exist, or other life might exist, but that other cosmic domains exist outside the space-time history we call our own. The word everything would become smaller. The night sky would look the same to the naked eye, but intellectually it would never be the same again. Every star would sit inside a bubble whose outer context we could not visit. Every human story would unfold in one cosmic pocket among others. Even the Big Bang would lose its absolute status. Or imagine that quantum gravity eventually shows that time genuinely emerges, not as poetry, but as physics. A deeper equation might describe reality without ordinary time, and our universe might be one classical history that appears when certain conditions are met. In that case, asking what happened before the Big Bang would be like asking what a melody weighed before sound existed. The grammar of the question would collapse, because it uses a concept that belongs only after the emergence. That discovery would be quieter than a multiverse, but maybe more disturbing. It would mean time, the thing we use to organize every experience, is not fundamental. Birth, death, memory, waiting, change, regret, hope, and cause all depend on time. If time is emergent, then the deepest layer of reality is not a world happening moment by moment. It is something from which moments arise. That does not make human life unreal. A wave is real even if it emerges from water. A temperature is real even if it emerges from molecular motion. A rainbow is real even if it depends on light, droplets, and an observer. But emergent things are not ultimate. They are patterns. And if time is a pattern, then the beginning of the universe may be less like a first tick and more like the place where the pattern becomes readable. That possibility changes even the emotional weight of the question. We fear the beginning because we imagine it as the first moment before which there was nothing. But if time itself is emergent, the origin may not be lonely. It may be timeless. It may be complete in a way sequence cannot express. The terror comes from trying to force it into the shape of a before. There is also the possibility that none of the popular images is correct. The true answer may not be a bounce, a black hole, a multiverse, or a simple quantum fluctuation. Those may be stepping stones, useful approximations, or wrong turns that helped build better mathematics. The actual theory may use concepts not yet invented. It may require a union of space-time, information, entropy, quantum entanglement, and geometry in a framework that sounds alien to the present generation. This has happened before. Before relativity, space and time seemed separate and fixed. Before quantum theory, particles seemed like tiny objects with definite properties. Before modern cosmology, the Milky Way was often treated as the entire universe. Reality has repeatedly forced human categories to widen. The origin may do the same again. Perhaps the deepest question will not be answered by looking for a previous event, but by understanding why information, geometry, and physical law are connected at all. Perhaps space-time emerges from entanglement. Perhaps gravity is not fundamental in the way it appears. Perhaps the Big Bang is a phase transition in a deeper structure. Perhaps the universe is not born from emptiness, but from a state where the distinction between something and nothing is not yet meaningful. These possibilities sound remote, but they are not random fantasy. They grow from real tensions in physics. Black holes connect gravity, entropy, information, and quantum theory in ways we do not fully understand. The early universe demands the same union. The cosmic horizon raises questions about what can be known. Dark energy shows that the largest scales still contain surprises. The problem of time appears in attempts to quantize gravity. The origin is not an isolated mystery. It is where many unfinished pieces meet. This is why a future answer may come from an unexpected direction. Not only from a telescope studying the microwave background, not only from a particle accelerator probing high energies, not only from gravitational wave observatories listening for ancient ripples. It may come from black hole thermodynamics, from quantum information theory, from mathematics, from simulations, from a new kind of detector, or from a contradiction inside an equation that forces a better idea. The road to before the Big Bang may not look like a road at first. It may look like separate trails scattered across physics. Then, one day, if we are fortunate, those trails may meet. Until then, the question remains suspended between evidence and imagination. That suspension is not a weakness for a story like this. It is the point. Because the universe is not terrifying only when it threatens us physically. It is also terrifying when it reveals that our deepest mental tools may be temporary. The same mind that can plan a city, love another person, repair a machine, write music, and recognize a face may still be poorly shaped for the question of ultimate origin. We can improve those tools. We can invent mathematics. We can build instruments. We can compare models. We can learn not to trust intuition when the scale becomes cosmic. But we may never make the deepest reality feel normal. And maybe it should not feel normal. A normal answer would be too small. The origin of space-time should disturb the categories that grew inside space-time. If it did not, we might suspect we had only explained a smaller thing. So the terror here is not panic. It is scale applied to thought. It is the feeling that every answer opens a larger room. It is the realization that the phrase "before the Big Bang" may point not to a hidden hallway behind the universe, but to the edge of explanation itself. And at that edge, the most important skill is not certainty. It is patience. Patience with evidence. Patience with incomplete theories. Patience with words that are beginning to fail. Patience with the possibility that the universe is not obligated to satisfy the shape of a human question. There is another detail that makes the mystery sharper. The early universe was not only small, hot, and dense. It was also astonishingly orderly in certain ways. Entropy, the measure of how many microscopic arrangements can produce the same visible state, appears to have been extremely low in the early gravitational universe. That may sound technical, but it touches the deepest reason time feels like it flows. A broken cup does not leap back onto a table because disorder is easier than order. Smoke spreads through a room because there are more ways for smoke molecules to be scattered than gathered. Stars burn because energy flows from concentrated forms to more dispersed forms. Life itself depends on usable energy moving through organized systems. The arrow of time, the difference between past and future, is tied to the fact that the universe began in a state from which entropy could grow. So before the Big Bang, or at the beginning of time, we must also ask why the early universe had the special conditions that allowed a future to unfold. This is not the same question as where matter came from. It is a question about order. Why was the universe not already maximally scrambled? Why was there room for structure to grow, stars to form, planets to cool, chemistry to develop, and memory to point backward? Some theories try to answer this through inflation. A tiny smooth patch could have been stretched into the visible universe. Others look to boundary conditions. Some connect the answer to quantum gravity. Some suggest that in a larger multiverse, regions like ours are rare but possible. But no answer has become final. This matters because without that early order, there is no story, no galaxies, no Earth, no fossils, no minds, no question about the beginning. The origin problem is therefore also the problem of why time has direction. When you remember yesterday but not tomorrow, you are touching a property of the early universe. When a star slowly uses its fuel, it is following the same cosmic arrow. When the universe expands and cools, it carries that arrow forward. So, if something existed before the Big Bang, it may have carried or produced the conditions for time's arrow. If nothing existed before it, then the arrow may have appeared with the universe itself. Either way, the beginning is not merely the start of matter. It is the source of the difference between memory and possibility. That is a difficult thought to hold for long. It means the past is not simply behind us because we happen to move forward. The past is behind us because the universe has a deep thermodynamic structure that makes records possible. Light from ancient galaxies reaches us as a record. The cosmic microwave background survives as a record. Rocks, fossils, DNA, and human memory are all forms of record. A universe with no arrow of time would not only be strange, it might be unable to contain stories in the way we understand them. This is why the Big Bang question cannot be separated from the question of time's direction. A beginning must not only exist, it must make history possible. And if that condition came from something deeper, then whatever existed before the Big Bang was not just a previous object or state, it was the hidden root of every before and after that followed. The question becomes almost too large. What existed before the Big Bang? Maybe the conditions that made time itself capable of having a direction. Maybe the reason broken things do not unbreak. Maybe the reason stars grow old. Maybe the reason a mind can remember the sentence it just heard and wonder about the one that comes next. That is why this mystery is not locked away in a remote mathematical corner. It is present in every ordinary experience of change. Every clock is downstream from the beginning. Every shadow moves because time has a direction. Every aging star is a quiet reminder that the universe was born with a capacity to spend order. And if we do not understand why that capacity existed, then we do not fully understand why there is a history at all. Perhaps someday, the answer will arrive in a way no one expects, not as a single dramatic announcement, but as a slow convergence, a gravitational wave pattern that fits one model better than the others, a particle theory that explains inflation without inventing too much, a quantum gravity calculation that removes a singularity, a map of the early sky that refuses to match the old assumptions. That is often how the universe changes our minds. Quietly at first, then completely. At the end of this journey, the most honest answer is not a neat picture. It is a set of possibilities arranged around a silence. Before the Big Bang, there may have been another universe. There may have been an inflating background. There may have been a quantum state. There may have been no before. There may have been a reality for which our words are only rough shadows. And still, from that unknown edge, this universe emerged into heat, expansion, atoms, stars, planets, oceans, life, and eventually minds capable of looking back. That does not solve the mystery. It deepens it, because whatever existed before the Big Bang, or whatever replaces the idea of before, it led to a universe where the question could rise from inside the answer. And that may be the most terrifying possibility of all.